So hi, I'm going to explain the bridge. So, an edge in an indirect graph is a bridge if removing it disconnects the graph. So, as you can see, I have an example here. So, yung mga naka-highlight dyan is yan yung bridge. If i-remove yan or i-erase, madi-disconnect siya sa graph. So, loops cannot be bridged because removing a loop from a graph cannot make it disconnected. So, if two or more edges share both endpoints, then removing any one of them cannot make the graph disconnected. Therefore, none of the edges is a bridge. So, yung loops na yan is, hindi yan siya bridge. If i-remove siya, hindi siya madi-disconnect sa graph. So, the Hamiltonian path. A Hamiltonian path or traceable path is a path that visits each vertex of the graph exactly once. So, a graph that contains a Hamiltonian path is called a traceable graph. A graph is Hamiltonian connected if for every pair of vertices there is a Hamiltonian path between the two vertices. So, in Hamiltonian path, as for example, my example dito, then mag-start siya from A and then going to C, B, D, E, F, G, to I, and H. So, the end point niya is sa H lang, hindi na siya magbabalik sa other vertex. Isang beses lang siya dapat mag-visit. And then, Hamiltonian circuit. A special type of Hamilton path which start and end at the same vertex. Example of Hamilton. So this is the example of Hamiltonian circuit. So as you can see, it is started from A to B and C and then going back to the A. Doon siya mag-end. From starting point to the end point is letter A pa rin. Same vertex siya mag-end and mag-i-start. Yun yung and then yung pinagkaiba nila is the Hamiltonian path is isang beses lang and di ka na pwede bumalik pa sa start para doon mag-end. Pero yung Hamiltonian circuit, kung saan ka nag-start, doon ka din mag-end. Okay.
So, for now, we will tackling about weight graphs. A weighted graph is a graph which each branch is given a numerical weight. A weighted graph is therefore a special type of label graph in which the labels are numbers, which are usually taken to be positive. In a mathematics and computer science, a graph is a collection of nodes or vertical connected by edge or branches. A weighted graph is a specific type of graph where each branch or edge is assigned a numerical weight. These weights represent some kind of value or importance associated with that particular edge. For example, let's consider a graph that represents a road network. The nodes could represent cities and the edges could represent the roads connecting these cities in a weight graphs. Each road is or edge would have a weight assigned to it, which could represent the distance between the cities or the time it takes to travel along that road. The weights could also represent other factors such as the cost of using that road or the capacity of that road. In the term labeled graph refers to a graph where each node or edge has a label assigned to it. In, in the case of weight graph, the labels are numbers, especially the numerical weights assigned to the edge. These labels provide additional information about the graph and help in analyzing and solving problems related to the graph. Um, it is worth It is worth noting that the weight in a weighted graph is usually taken to be positive numbers. This is because negative weights can introduce complexities and challenges in certain graphs, algorithms, and calculation. However, in some cases, negative weights may have some specific meanings and how can use in specific scenarios. In summaries, a weighted graph is a graph where each branch or edge is assigned a numerical weight representing a value or importance. It is a special type of labeled graph where the labels are numbers, typically positive. These weights provide additional information and enables various analysis and computation on the graph. Some uses of weighted graphs. Weighted graphs can be used to model the following. First, maps with weights representing distance. In the context of maps, a weight graphs can be used to represent distance between different locations. Each location is represented as a node, and the edges between the nodes are assigned weights that correspond to the distance between those locations. These weights can be measured in various units such as kilometers or miles. By using a weighted graphs, we can calculate the shortest path or the most efficient route between two locations on the map, taking into account the distance represented by the weights. Second, water networks with weights representing water capacity of pipes. In the case of water networks, a weight graphs can be used to model the flow of water through pipes or channels. Each pipes or channel is represented as an age in the graph, and the weight assigned that age represent the water capacity of the particular pipe. The weight could be measured in terms of volume or flow rate, indicating how much water can pass through the pipe. By analyzing the weight graph, we can determine the optimal flow of water through the network considering the capacities representing by the weights. Lastly, the electrical circuits with weights representing resistance or maximum voltage. In electrical circuits, a weighted graphs can be used to represent the connection between different components, such as resistors, capacitors, and sources. The age in the graph represent the connection between those components, and the weights assigned to the ages can represent various electrical properties. For example, the weight could represent the resistance of a resistor or the minimum voltage that can be applied across a certain component. By analyzing the weight graph, we can analyze the flow of current and voltage in the circuits, taking into account the electrical properties represented by the weights. In summary, maps can use weight graphs to represent distance between locations. Water networks can use weighted graphs to represent water capacity in pipes. And electrical circuits can use weighted graphs to represent resistance or minimum voltage in components. These weight graphs provide valuable information for various analyses and calculation related to their respective domains. Dijkstra's algorithm. Algorithm is an algorithm for finding the shortest paths between nodes in a graph. Dijkstra's algorithm is a popular algorithm used to find the shortest path between nodes in a graph. It was developed by Dutch computer scientist Edgar Dijkstra in 1956 and has since become a fundamental algorithm in a graph theory and network analysis. The algorithm works by iteratively exploring the graph from a starting node to all over reachable nodes, updating the shortest path's value as it progresses. Here's a step-by-step explanation on how Dijkstra's algorithm works. First, start by assigning the tentative distance values to every node in the graph. The starting node has a distance 0 and all other nodes have initial distance of infinity. Second, select the node with the smallest tentative distance and mark it as the current node. Third, for each neighbor of for each neighbor of the current node, calculate the tentative distance from the starting node. This is denoted by adding the weight of each connecting the current node to its neighbor to the tentative distance of the current node. If this calculated distance is smaller than the neighbor's current tentative distance, update the next more tentative distance. Fourth, once all the neighbors of the current node have been visited, mark the current nodes as visited. Fifth, if the destination node has been marked as visited, or if the smallest tentative distance among unvisited nodes is infinity, the algorithm is complete. Otherwise, go back to the step 2 and select the node with the smallest tentative distance as the new current node. Lastly, the algorithm completes the shortest path from the starting node to any other node is in the graph can be determined by backtracking from the destination node, following the nodes with the smallest tentative distance. Dijkstra's algorithm is commonly used in various applications, such as finding the shortest route in transportation networks, optimizing network routing protocols, and solving resource allocation problem. It is an efficient and reliable algorithm for finding shortest paths in graph, although it may not work correctly with negative edge weights. Um, Create a set SPT set, also known as shorted path tree set, that keeps track of verticals include the tree shortest path tree. Initially, the set is empty. The shortest path tree set will eventually contain all the verticals or the vertices for which the minimum distance from the source vertex has been calculated and finalized. Second, assign a distance value to all vertices in the input graph. Initialize all distance values as infinite except for the source vertex. Set the distance value of the source vertex to 0. This ensures that the source vertex is picked first for further processing. 3. While the SPT set doesn't include all vertices in the graph, continue the following step. By A, pick a vertex U that is not in the SP set and has the minimum distance value among all the vertices not yet included in the SP set. This means selecting the vertex with the smallest tentative distance value from the source vertex. B, including the vertex U in the SPT set, indicating that minimum distance value has been finalized. C, for each neighbor, V of the selected vertex U that is not yet included in the SPT set, calculate the tentative distance from the source vertex to V through U. This is done by adding the weights of the edge between U and V to the distance value of U. It is calculated distance is smaller than the current distance value of B. Update the distance value of V to the new smaller value. D. Repeat the step A, B, C until all vertices in the graph are included in the SPT set. After the algorithm is complete, the shortest paths from the source vertex to any other vertex in the graph can be determined by examining the calculated distance values and the path through the vertices with the smallest tentative distance. Dijkstra's algorithm guarantees that the shortest path from source vertex to any other vertex is found, provided that the graph does not contain negative edge weights. It is widely used algorithm for solving the single source shortest path problem in the graphs.
Hello everyone, I'm Nur Aisha Sam and I'm going to tackle the platonic solids. So what is platonic solids? Platonic solids is a convex polyhedron with all of its faces, regular and congruent, and with all of its vertices having the same degree. So they are exactly 5 platonic solids. These 5 unique shapes have been studied by many mathematicians for 1,000 of years, and they have been named after their great philosopher Plato. So Plato have studied the role about the platonic solids in his dialogue, which is the Timaeus, 360 BC. So let me introduce you the 5 platonic solids So the platonic solids represents the five elements, which are the building blocks of universe: fire, water, earth, air, and the fifth one being universe or ether or prana, whatever you want to call it. So now each of these elements have unique criteria. They're created with the same edge length, the same phase, the same angle, and all the vertices of each solid fits inside the sphere. So let me discuss each platonic solids in detail. So we're going to start the tetrahedron. Tetra means four faces or four equilateral triangles. The second one will be the cube or hexahedron. Hexa mean they are six faces or six identical squares. The third one is octahedron. Octa means they are eight faces or eight equilateral triangles. The fourth one is dodecahedron. Dodeca means they are 12 faces or 12 identical pentagons. And the fifth one, the last one, will be the icosahedron. Icosahedron meaning they are 20 faces or 20 equilateral triangles. So the tetrahedron will represents fire as dyan na sa taas. So the hexahedron or cube represents earth. The octahedron represents air. The icosahedron represents water. And the last one is dodecahedron represents ether or universe or prana. That's all. Thank you.
Hi, I am the next presenter. Graph coloring. What is the graph coloring? A proper coloring of a graph is an assignment of colors to the vertices of the graph so that no two adjacent vertices have the same color. Ang graph coloring ay ang paglagay ng kulay sa mga vertices ng graph. For example, you have 4 vertices of the graph. In the vertex 1, 2, 3, and 4. Then you put different color of it. So walang mga adjacent nga na pare-pareho ang kulay. That is the graph coloring. Let's move to the vertex coloring. Vertex coloring. A vertex coloring of a graph is an assignment of colors that vertices of the graph so that vertices that are joined by an edge, adjacent vertices have different colors. Vertex coloring naman ay maiihan tulad natin sa graph coloring. Pero dito sa main focus of it are the vertex. As you can see, the graph has been labeled as 1, 2, and 3 in its vertices with different color. Let's say we put yellow on the 1 and blue on the 2 while green on the 3. When you have the same color of vertex in one graph, it is a main na magkakapareho vertex sa isang graph. Chromatic number. What is the chromatic number? Chromatic number of a graph is the minimal number of colors needed to color the vertices in such way that no two adjacent vertices have the same color. The chromatic number of a graph G is the minimum number of colors required in a proper coloring. The independent number of G is the maximum size of an independent set is denoted G. Why not? Yeah.
Hi everyone, I'm Shyam A. Abdullah and I'm going to tackle the 4-color theorem and the 5-color theorem. So first is the 4-color theorem. So 4-color theorem or the 4-color map theorem state that no more than 4 colors are required to color the region of any map so that no two adjacent regions have the same color. So adjacent means that the two regions share a common boundary curve segment not merely a corner where three or more regions meet. So many simpler maps can be colored using three colors. The fourth color is required for some maps, such as one in which one region is surrounded by an odd number of others, which touch each other in cycle. So next is the five-color theorem. So five-color theorem states that any map on a flat surface, such as a sheet of paper, can be colored with a five color in such a way that no adjacent region or countries have the same color. So this requires only five colors. So this theorem is generalization of the four-color theorem, so which asserts that the four colors are sufficient for any flat map. So the five-color theorem is result in the graph theory and has application in cartography and map coloring problem. So that's all. Thank you.
Graph planarity. The planar graph defined. A planar graph is a graph that can be drawn so that no edges intersect each other except at vertices. If the graph is drawn in such a way that no edges cross, we have a planar drawing of a graph. So dito sa right side natin ay meron tayong graph na merong 6 vertices at meron din tayong 6 edges. So this is a connected graph. So ngayon, bakit nga ba siya tinawag na planar graph? Because according to our definition, wala tayong nakikita na intersection dito sa gitna o sa labas man ng mga edges. Except nagtatama lang siya dun sa mismong vertices niya, di ba? So this is considered as a planar drawing of a planar graph. So next, dito naman tayo sa second example natin. Dito sa pinaka left side, meron tayong graph na merong 5 vertices and yung ating 9 edges that connect this graph. So this is also considered as a connected graph kasi all vertices niya ay connected, di ba? So merong paraan para mawala yung mga intersection na to at gawin siyang planar. Kasi kung makikita nyo dito sa part na to, nag-intersect yung dalawang edges niya. Dito rin nagkaroon din ng intersection. So, ang gagawin natin, papalitan natin yung color ng dalawang edges na to. So, dito naman, sa part na to, iniba na yung kulay niya, which is kulay pink. And then, dito sa last part naman na to, yung ginawa ay in-stretch out niya. Kunyari, rubber, parang rubber siya na kaya mong higitin palabas. So, ayan na yung kinalabasan. Yung nangyari, lumabas na siya na ganyan. Pero, yan pa rin yung edges na yon. Wala namang pinalitan. Ngayon, mapapansin mo na nawala na yung mga intersection niya, di ba? So, yan na yung tinatawag nating planar drawing. The next is Euler's formula. Leonhard Euler noticed that there is a connected between various features of planar graphs. In addition to edges and vertices, he looked at faces of a graph. In a planar graph, the edges divided the graph into several regions called faces. The region surrounding the graph or the exterior is also considered a face called infinite face. So let's take a look at an example. So dito meron tayong example ng planar graph na merong 6 vertices, 7 edges, and meron tayong 5 faces. The formula is a connected graph with no intersection edges. Let V the number of the vertices, E the number of the edges, and F number of the faces. Then, vertices plus faces equals to edges plus 2. So, tignan natin ang vertices natin is 6. Ang faces natin ay 5. So, 6 plus 5 equals 11. And yun na nga, yung edges natin ay 9. So, 9 plus 2, 11. O, di ba? Tama. So, yung formula is always true. So, sa second example natin, bilangin natin yung vertices. 1, 2, 3, 4, 5. Faces, 1, 2, 3, 4. At saka yung nasa labas, 4. Infinite face, so that's 4. And yung edges niya is 1, 2, 3, 4, 5, 6, 7. So add natin, 5 plus 4, that will be 9, is equals to 7 plus 2. O, diba? So, the formula is always true.